Hey everybody, this is Larry. This is day 18 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Today we have 2401 longest nice subarray. You're given us an array nums consisting of positive integers. We call a subarray nums. Oh yeah. Hey everybody, how's it going? Uh, Today I'm really tired. I just ate a lot, so I'm a little bit of a food coma. I did work out. I did push my. It's not a PB. It's not a PR. It's not a record or anything. But I did my squats. It's my annual or this year's personal best. I think that's how I get up to it. So yeah, just like 5 pounds over. So I'm just trying to do a linear progress to see how long that will last. We'll see, because I feel like my back's a little bit the limiting factor, not my legs for squats. So I have to figure out what that means. But yeah, that's it. So let's take a look at today's problem. We have okay, subarray nums is nice if the bitwise end of every pair of elements in there are in different position in the subarray equal to 0. What? We call a subarray of nums nice if the bitwise end of every pair of elements that are in different position in the subarray is equal to 0. What? Oh, I see. That is such a. I mean, I'm sure it's precise, but still very awkward. Return the length of the longest nice subarray. A subarray is contiguous part of a subarray. Okay. The first thing I want to look at is just bounds. Bounds is n to the 10 to the 5th, which means that, I mean, just to be clear, n squared is not fast enough. My first intuition may be sliding window. Yeah, my first intuition would be sliding window. But the question is, can you do the slide in constant or log n time, right? That I'm not super sure about. So there is some invariant, right? Is that, let's say you start with the number 3, you add the 8, well, 3 and 8 is going to be good, right? So when you add the 48, you don't have to check the 3 and 8 again, but you still have to check the 48 and 3 and 8, right? So I think, I don't know that if there's a easy way to check it. If that was the sliding window. Another way that I could think about is maybe binary search, right? Starting from any element, we can see how far we can go to the left. But I'm not sure that handles the bitwise portion, right? So maybe we have to figure out how to, oh, not the bitwise, sorry, pairwise, for every pair of elements. Right. So we have to figure about the pairwise operation. All right. I think given that this is a bitwise operation, I think one thing that I would explore initially is just limiting it by looking at one bit at a time, right? I think that's the way that I'm thinking about bitwise operations. And here, I think that becomes clear very quickly, actually, right? Because basically, what happens, right? What happens is that if you look, and I think that is the way to simplify this problem. Otherwise, it just gets a little bit difficult, confusing anyway for me. I didn't know how to do it immediately, but this immediately showed me. I mean, even without going through it, I think it visualized, right? Because basically, if you have one bit, right, if you look at one bit at a time, then that means that everything could be only be 0 and 1, right? That means that if all in the previous is 0, right, and then now you add a thing that has, and of course, all this will be pairwise, not bitwise. I mean, also bitwise in this case, but pairwise, n will be 0. But we add a 1, still true, right? But then now, if we add well, we add 0, it's fine. But we add another 1, then what does that mean? That means that well, 1 and 1 will, no matter what position it is, the pairwise end will never be 0 because you only need what happened? You only need one position to have 1 in one place to have it not equal to 0, right? So okay. So yeah. So that's basically, and that's all I need, right? Because this kind of, and there are a couple of ways you can solve this problem, I think now. I mean, sliding windows is one. I think it actually reminds me of the problem that we had a couple of days ago with the, was it ABC or something? Like you're trying to find the last A, you're trying to find the last B, and you're trying to find the last C. This is exactly it, right? On the bitwise position, or the bit shift, if you will. Because that means that now you check it for the shift of 0, because every binary number, maybe you can think about this as say 2 to the 0, right? Oops. And every binary number you can just stack them on each other in some way, right? 2 to the 1, right? And then dot dot dot. I don't want to draw all of it, this is just random anyway. But that means that here, when you have a new number, if coming up, if this is a 1, that means that you have to look at the previous time that you see a 1 and you try to get the max out of them, right? So this is, and here if you see a 1, then we know that everything left of this is a cutoff, right? So this is exactly what we were doing with the ABC problem, right? And kind of just, I guess we had a couple of binary search problems, so maybe it wasn't last week, but because I forgot last week was binary search. But there is like one like this, right? I'm not dreaming of this. Hopefully not. There was like an ABC one, not this one. That one was hard. I still don't know how to. Not alternating groups. Did I make that up? Maybe I made that up. Where did I know this one? Did I do it like in a weird thing? Oh no, this one, right? Yeah, I just missed it. Number of substrings containing all 3 characters, right? Except for in this case, it's the longest, and instead of 3 characters, it is instead of 3 characters, it is just 32 bits, or what is it? 10 to the 9, so 32 bits, right? So yeah, so I mean, we can do it. I mean, I'm going to do it without the heap, just like the way that we had before. But I think that is the idea, right? Because because it doesn't matter what the thing is that here, because you want the pairwise bitwise end to be 0. It doesn't matter if you have these 2 ones here. It doesn't matter what the rest of the digits are, because the pairwise end will never be 0 in that case anymore, right? Okay. So yeah, so then now if we want to write it that way, then we can just write for x in nums, or maybe enumerated, so we get the index, right? And then maybe we have a last array, which is just, let's just say -1 times 32, right? And yeah, and then now we go, and also we keep track of best as the longest, right? And we just set it to 1, because I don't think, unless 0 is in valid input, or 0 element array is valid input, then you will always get 1. But I think that's fine either way. You can also change it depending on. But yeah, then now we go, okay, so let's just convert this to B for bits, right? For J in range of B, if if this offset is greater than 0, then last of J is equal to index, right? But before we set it, it means that now before we set it, I think I mean, there's some order of operation that I'm trying to think for, meaning that I think we have to check it first, and then yeah. Yeah, so actually it is only the max of all the elements in which there is a 1, right? Because if you have a 0, you don't care what the last one is because you can go past it anyway. Well, that's not true. That's a little bit awkward, actually. No, because because for example, if the answer is like 0, 1, 0, 0, 1, and then more zeros, and then now you have a 1 here, then actually you want the last one has to be here no matter what, right? So we have to keep track of that. Yes. Okay. So we have to be a little bit careful. Yeah. How do I want to write it? I mean, it's not that bad, but I'm just trying to be lazy. Because I think we can just put it in a stack. I think that's it. But with a stack, remember, you have to write it like this, because otherwise it's the same reference, right? So then now we can say, yeah, maybe last dot append, or last sub j appends index, right? And then now we do an other loop, right? So if this is true, then before we occupy this, then we want actually no, I guess it doesn't really matter, right? So then now we do this, and then maybe we keep track of the rightmost, right? So rightmost is going to be equal to 0, say, just for whatever, or -1, maybe that's a little bit clearer. And then here, if there's a 1, even if there isn't a 1, I think we have to check for the second to largest, right? Because that's the cutoff. Because basically, and that includes appending the current one. So that means that if length of last is last of j is greater than equal to 2, then rightmost is equal to max rightmost, or last of j of -2, which means the second element, right? The second index that we care about. And then now best is just equal to max of best index minus rightmost, maybe +1. Because that's the rightmost of a 1. So no, you don't include this one. So I think this is fine. Yeah. Okay, I forgot to define B. Right, so I think that looks okay. So let's give a quick submit. Hopefully we're no silly mistakes. But yeah, I think this definitely has a potential to be a tricky one, right? But you just have to be a little bit careful. I don't know why this is so slow though. I would have imagined it not be that bad. I mean, we are just linear time, right? So, let me give it a second of thought. Maybe I could because usually I don't mind being a little bit slow, but this is really slow, right? Because this is just one bit at a time, and I mean we do an append, sure. And maybe we allocate memory, maybe that's why, but that's still linear in the size of the oh no, it's linear times 32 possibly. So maybe we need this to be, I don't know, something like this. And then yeah, so yeah, maybe do we just try like but I don't know that that is I don't know that this is that much faster. Let's give a YOLO submit. I'm just guessing on the thing. It may even be same/slower, yes. So it's not the memory that's the issue. But I don't even know why. It's not that slow. Is there a cleaner way of thinking about it? Maybe there's an upsolve opportunity here. I mean, this is definitely a solution, but it's still not great. I mean, usually, like I said, I don't mind a couple little bit, but this is an order of magnitude. So I mean, maybe you don't need the bit thing, even though this is without a doubt correct because we did submit it and it's correct. But how would I think about a better way of thinking about it? I have a new one. I don't know. I mean, even just like I don't feel like these are very expensive operations. Maybe the max. Let's see. That'd be funny if If that is the reason. I mean, I'm sure it helps a little bit, but I don't know if it helps too much. Let's give it a submit. We'll see how right I am about it helping. Okay, I mean, it helps a little bit, but actually less than I thought it would. I mean, in terms of implementation, I don't see anything too obvious. In terms of ideas, maybe there is one. Right? Is there a binary search idea? Yeah, so arrays are faster. We don't have to create a queue object, which has a thing, but I mean, the way that I would have maybe guessed would be to use a heap or something, but we're looping anyway, then you know, like this is not like you don't need like you can just do this because we're looping anyway, right? So there's no point of not like using adding a log n factor, or I guess in this case just log p factor. This is gonna be all be in the worst case, but I am curious, what am I doing? Is there a dumber way, naive way of handling this? I solved this before. I have solved this before. Did take it. I mean, even last time it was faster. So, I mean, I guess another way that we have to think about is maybe there's another property that we can abuse. This is one of them. Right. So okay. So maybe it is just sliding window. But even but maybe without the bitwise thing, right? With the sliding window, we go. You remove. Right? I mean, so what is the invariant, right? That means that adding this number now imposes, but that is basically what I'm doing, right? I mean, this isn't quite sliding window in the strictest sense, but it just moves the window a lot. Like maybe we could get rid of this function max with some assumption, but that's still going to be n times b, which is where I would imagine is some of the cost. So that means that there is a way to do it without the b factor. So we have to figure out, that means, is there a binary search? Well, okay. So can I right? So we assume that. Okay, so if we go back one element, we assume that all the bits that it has does not. Okay, so the invariant is that, like we said, if we have 3 and 8, if we add 48, we don't have to compare to everything else, right? But 48, that means that we can, if we have a way to kind of check bitwise between 48 and 8, but that means that in a bitwise AND situation, 48 and 8 is still going to be 48, right? Or 48, how do I write this? I mean, the AND will obviously be 0, but is there a way to keep building in a prefix sum-ish kind of way, right? I think that's what I want to know. Well, I mean, is it prefix sum? It just means that Okay, I mean, if we do a sliding window, but it's still, so the thing I'm thinking about is just that we can do a sliding window and then do a count, right? But that's still going to be bit by bit, right? On the right side and on the left side. So how would that be faster? Like the way that I would think about a sliding window would be just like the count of ones in that thing, and the count of ones in that bit has to be 1, right? So maybe another way you can think about this is that yeah, so maybe you could just say count of bits, which is equal to 0 times 32, right? So that's your sliding window. And then maybe you could say, what's going on? Let's just go this right for the right, if I could type it correctly, and then left is equal to 0, right? And then if you want to do sliding window, then it is just, yeah, now we add the item, right? So for j in range of b again, which I don't know if this is good enough, but if this is greater than 0, then counts up j increment, right? Yeah, and then maybe we have a yeah, I mean, I guess I don't know, like we could do it afterwards. Okay, fine, right? So that's just for increment. I mean, I want to separate this out just so that it's a little bit cleaner or clearer anyway. I don't know. So if counts of j is greater than 1, then good is equal to false, right? So while not good, we have to yeah, so we decrement. So this is sliding window, right? But and this is actually, let's just call it y, for y is equal to num sub left. And then remember to increment left, Larry, okay? And then count of j, right? And then good is equal to true. And then if counts of j is still greater than 1, then good is equal to false, right? And then we just keep going. And then best is equal to max, best, right minus left plus 1, right? Something like that. Oops. So that's the way to do it with sliding windows using another idea. Let's go submit. But I can't imagine it'd be that much faster, right? Because it still does the loop of 32 bits, and then you have. Is there another way to think about this? I see. Maybe. Well, I mean, I guess the idea would be to do it all at once, right? So you don't really need to count, you just need to slide the window, because all this can only be 0 and 1, really. I mean, because here, there's no way, if it goes from, it cannot go, if it already has 2, you would have already, yeah, it cannot be more than 2, so then maybe you could have a bit mask of the like current bit mask is equal to 0, right? So here, then now, we want to say it, while current bit mask, n x, if this is greater than 0, that means that we have to shift left, right? Because that means that adding the current x would make one of the things 2. So then here we want to shift left, so current bit mask, we want to take out the left side, right? So that means we want to XOR the flip of num sub left, right? Something like that. And that's just to flip the bits off. So I'm not explaining that well. I'm just trying to make sure that this works. And then now we can do current bit mask. We want to flip it, right, of x. And also, I guess we don't have to change the other thing. So yeah, I guess that's why maybe, but current bit mask, num sub left. Why would that? Current bit mask is 0. We set it. Maybe I don't flip this on correctly. Oh, turn this off. Oh no, this is an and. Whoops. Yeah. Whoops. I mean, you have done it in either way, but I think that's the way. I guess that's how you get it so fast. Yeah, now this is much faster. Even though it still doesn't beat as much, but you can see so. But that's because we do it all at the same time, which is kind of a, I don't know, a funny requirement perhaps. But honestly, all the ideas are the same. It's just bitwise operation you get to do it in parallel. Yeah, this is kind of a long video, even though, of course, as you saw, we got the right answer about 12 minutes ago, but it's just about this optimization. I don't know that I care that much about this optimizing, honestly. It doesn't change the problem, really. It's just, I don't know. It's just like a very minor syntax. Is it syntax? I don't know. But it's just like a not very interesting. At least for me, it's just not very interesting. But it's worth doing it once, I guess. But yeah. Yeah. Anyway, that's all I have for this one. Let me know what you think. Thanks for watching. And yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.